So this is week 9. So though the week 9 was our midterm, but for the teaching, it is still week 9. And today we shall be covering supervised learning and deep learning. So let's see. Uh, and your Ahmed Saab is saying that kindly submit your assignment on time. He is still receiving requests to extend deadline for assignment number 5. We got to be perhaps a bit strict about submission of assignment. So you kindly submit the assignment on time, uh, as it becomes really hassle for him to keep receiving assignments and then just keep extending the deadline. So we start from a review of the outline of week 8, where we learned about Gaussian mixture models, and then extended that to generative AI. Just saying that it's almost the same. The models that you got to um, extract from the data, which apparently is not an easy job. So then we also covered clustering, evaluation techniques, and then move to supervised learning. And we cover something which is very basic, which is naive-based classifier. This week, I want to dedicate uh, the week to Professor Dr. Andrew Ng, and let's see why, and also let's see what are the basically uh, outline for uh, this week 9. So we are going to find out more about Dr. Andrew Ng, and primarily his perception of AI and the future of work. And then I want to just cover a few more examples real quickly of naive-Bayes classifier. And then we will just extend our discussion to supervised learning, class of algorithms. And again, we will start with covering something which is very, very basic, which is KNN, K nearest neighbor. And then we will learn about that how once you are in a supervised learning environment, like in that case, we did the evaluation criteria, that how do you evaluate a cluster and the results. And here we, because it's supervised, so we need to say how do you supervise, how do you train a network, how do you validate your model, and then finally how do you test your model. uh, that shall take us to uh, an example of image classification and to learn about neural networks, and then also to learn about deep learning, which primarily we shall be focusing on convolutional neural networks, and which has been, as you know, very so people are very have been using the convolutional neural networks in many application. Perhaps it is ease of use, and you will find many research paper, thesis, projects talking about CNN, convolutional neural networks. So this is the outline. So let's first find out who this Dr. Andrew Ng is. So if you go and search for top 10 AI leaders today, you will find his name at top of the list. So means that he's worth uh, finding that what his perception is, what his contributions are. So, and then you find out that he is primarily a computer scientist and entrepreneur, and widely recognized as a world leader expert on artificial intelligence. So he's founder of deeplearning.ai, where he teaches, so you can take a course, a short course, learning about skills on going to this website, deeplearning.ai. He's a co-founder of Coursera. I hope that all of us know about Coursera. And like Google, China has its own search engine, which is Baidu. So he was a former vice president and chief scientist at Baidu. And also Google Brain, which is where the AI happens in Google. He has been leading Google Brain team. And then he has two other entities, Lending AI and AI Fund. I think somebody's mic is on, so If you could just turn off all the mics, and anybody who wants to ask a question, then perhaps you may turn your mic on. So here is what is there on lending AI, and this is very very interesting, and I am really surprised because it's precisely what we are. So this talks about building computer vision system in minutes via natural prompting interactions. So this is landing AI. It talks about that how can you just give prompt and just develop a computer vision application, and this is what we are learning in this course as well. And I find a lot of really motivation similarity of what we have been just focusing, stressing, and what Andrew Ng believes and has been practicing. And we will find out a little more about that. So he has also started this AI fund, and he says, together, let's build great companies that move humanity forward. And he is leading AI fund as a managing general partner. So you can find many of his talks about what is this fund about and who they fund, uh, and how does he believe that funding, instead of just making a big company, funding small ventures, and many of them is better. And then this is where he was at Bedu and Chinese search engine, and he this is where he founded and led the team at Google Brain. And this is what he says. He says AI is the new electricity. So like electricity is used almost everywhere in our home appliances, to lit the roads, and to the industry, and to almost everywhere you find electricity. So he believes that AI is going to be the same, and AI is going to change this world and change the way people work. And so this also kind of reminds me of Iqbal, who says, "ये कायनात अभी ना तमाम है शायद, कि आ रही है दमादम सदाए कुन फयाकून." Like a new world has is always on can be just created, uh, perhaps because this world is not complete yet. So this is his view that AI technology current, he according to him, and he has not given any statistics, but he believes that most of the AI is in this space, which is the supervised learning. So this is the supervised learning space. And let me just turn on my pen. Here is the pen. Okay, yeah. So it is this space. This is the supervised learning, and this is a much bigger space. And then is the generative AI, which is just started. So it is just started, and this has been happening for last many years. And this is unsupervised learning that we have learned about clustering, the k-mean, and the Gaussian mixture model, and other. And there is something which has been just staying very small for last many years, and it had big promise, but it has not really come up to the promise. This is the reinforcement learning. So most of the focus has been of the industry, especially has been on supervised learning, that we have like kind of started learning from last lecture. And this is what he believes what is going to happen in 3 years. In 3 years, he believes that it will almost double the area, because it is the area. So this is going to be double, and he believes that this will even increase more than double. And unsupervised learning is also going to increase, and a little more into reinforced learning. But primarily, from the business perspective, from the innovation perspective, from the startup perspective, he believes that this is still going to be an area of focus, and we will find out why. So if you remember that we covered the unsupervised learning, which has data and creates a model, and this model then you can use to do the generative AI, generating more data, which is not really in your. So it can just generate more data, the generative AI of this type. Whereas here, the supervised learning is different, because here you have data and you also have label. So you have many data samples, you have many labels for each data sample, what it corresponds to. If it is patient's data, so you know that why the patient is there, the disease, and if it is about an object, so what object is there. So you have this label data and you try to develop a model. In model, you split your data into training and testing, and training data you train. So the model will output y model y, and here you have the actual label, and then you compare. If they are not the same, you generate an error, and the error goes here and tries to update the model. So you put a line that the model keeps getting updated, and you spend a lot of time, and sometimes many days, sometimes many months, sometimes many hours, depending upon how much data you have and how complex the model is to train this model. And then finally, once you're happy, then you can just deploy it. Uh, so this is again, according to Professor Andrew, prompting. Prompting is revolutionizing AI application, and that is what we have like doing in this course. This is what we have done even in our midterm exam. It is the prompting that is going to revolutionize. And why he believes so? He says in supervised learning, uh, even for small application, you need to spend a lot of time in getting the label data or to label the data yourself. And whatever application you're targeting, you got to label the data. And then you have to train the model training, all the iterations, and going back and finding out more data would take you 4 to 5 months. And then it is only then that you deploy the model, another 4 or 5 months. So it is about 12 months, and he thinks that if 12 months a team which we have to put on this for 12 months, and it is going to cost you a lot of money. So many applications are yet not realizable because of the small volumes of the application and the amount of money it will take to put a team together that can develop an application in 1 year time. But now he believes that with prompt based AI, it is almost instant. Can just input a prompt and directly generate a trained model, which then only you have to deploy and see that how it is performing. So it is a matter of minutes or matter of hours that you can have a model ready to be deployed. And that's the beauty of what we are learning in this course. And this is what the Andrew NG also believes, that this is what the future is. And now, but only you have to find out more applications. And so where the money is, this is important, that where can you just target and what should you target to earn money on what you are learning today in this course. So he divides this, makes it a decaying exponential. So this is a decaying exponential of the value AI can create. So this is the value, and this is the AI can create. And here is AI application that creates humongous amount of value. It may be into trillions of dollars or billions of dollars or trillions of dollars worth of value. It is only if a piece of code you write, one application being used by millions of people. Like Facebook is an application which is used by almost everybody on, at least in Pakistan, on the face of earth. And Twitter is such an application. Okay, Google is such an application. One piece of code. So one piece of code being used by almost everybody creates a lot of value, but it is almost, just sitting in Pakistan. I'm not saying we must not attempt to find out and to develop application which could be adopted by everybody. But then he believes that most of it is at the tail, where the tail is where AI can create a low value, but still significant. He believes that you can easily create from $5 million to $10 million worth of business, which from our perspective is a lot. And you target this, where you apply AI potential projects sorted in decreasing order of value. So you basically target the tail. The tail are the applications where there may be only hundreds or thousands of users would be using it, and obviously you're targeting. So he gives example of a pizza maker where the AI can help him to just spread the cheese uniformly on the pizza. And so like very small businesses where you can increase their efficiency by putting an AI engine. So almost any business, may it be supply chain management, may it be manufacturing, may it be services, may it be finance, may it be accounts, may it be anything. He believes that you can just add value to what they do using AI very quickly. So you go, you just make a demonstration, make a model, go and show them. And definitely that requires you to collect label data, because you are basically helping a business to grow. So you need a label data. Okay, if it is a hospital, patient records. If it is a transportation services, the schedule, um, the timing, the number of customers who usually are serviced. And so you got to have the label data about that business. So you still go find out the label data, instantly create a model, and then you go back and show it to the customer that this is what the value you can add. And that's how you can have make a lot of money using this low or no code tools that we are learning in this course. So interesting it is. uh, so this brings us to the second part of the lecture, which is about the knife base, though we covered it, but let me still uh, okay. So so we need to just cover a few more examples, and because this is our first uh, supervised learning tool that we have learned. It is naive based classifier, which is supervised learning, and we have already covered that it uses Bayesian theorem, and it is naive because it has this rigid requirement of on all the features that they are independent of each other, but usually they are not. In almost any application they are not. So though this is the formula, but I would rather have to show you this one, where once we say you have label data only means that you have an X. So X is your sample data, so many data points. Okay, so many data points X. So it is like usually it has D dimensions. So it is a D dimensional data. And maybe for a patient, it is his weight, it is his height, it is his blood pressure, and maybe other tests that you have taken. So these are the dimensions. So I is the first patient. So this is patient number one. Then you have the same set of data for patient number two, patient number three, patient number four. And for example, if you're checking whether the guy has diabetes or not, so then it is labeled data. I say, no, he is no diabetes, no diabetes, yes diabetes, yes diabetes, no diabetes, no diabetes, yes diabetes, yes diabetes. So this is once I say that you got to go and collect label data to make something valuable to a business, that you go find out what data you got to collect and how that data primarily is got to be labeled data. Customer just getting into a shop and not buying anything, for example, but customer getting into the shop and buying something, and you have his mobile number, you may have his Facebook profile and Twitter profile, where you can collect some more data. So you can have like some of these points here. And then and then also you may have in the label data whether he buys something small, something big. So you got to be creative in finding out how to collect once you are targeting a business and going to a business and telling them that you can improve their performance, their profitability, and then you got to tell them how you are going to do that. And that's how that you got to collect data, which is a label data. And maybe first thing is that definitely you try different models. This you should also remember that you can try different models. So this is where you already know. So these are the label training samples. For every X sample, the output. So for every output, that for this output, the person who bought something from your shop is yes. So output is yes, he bought something, and access is customer data, whatever you could collect. Okay, and then you can find out that given that who are the patient who have bought something and who are the patient who have diabetic, and their probability that if given that they so you find out the distribution of X, that who are those people, maybe their salary. So then in that case, it'll be Gaussian, that the people who are buying something from the shop, and if you have access to their salaries and you say, oh, these are the people who have bought something. Okay. So you can basically find out a distribution. The probability of them buying something is what, or if it is just few samples, then you can find out the frequencies, and that what is the probability of somebody whose salary is 20,000 rupees to buy, what is the probability somebody who has a salary of 30,000 rupees will buy something, because there came like 10 people with 20,000 salaries, 7 bought something and 3 did not. So definitely it will be 7 over 10. So that's how you just, for every feature you have treat it independently. You have a label here. So you have, so you can make another table of the weight, similar weight people, or is weight in the same bracket. So you say people with 60 kg to 70 kg, and there are 98 people. And out of those 98 people, you divide them like 70 and 28. 70 people have diabetes and 90 people don't. So this will give you a probability. So given Y, you can find out the probability X. Okay. And out of the whole population, this is priori probability. You will find out that you have data of 1,000 people, that what is the probability that people have diabetic and what is the probability people don't. Usually we need not to have this, the denominator, which is common to whether somebody has diabetic or somebody does not have diabetic. So because the denominator is going to be the same, so you don't need to calculate this. And now comes a sample. Given a sample, you need to find out whether this guy or a person enters in your shop. Okay, and if you have a good model, you can tell that this person, if you know a little about him, is going to buy something from your shop, and say, wow, this is going to buy, so you'll give him better service. Okay, so that's how the value you add into your business, by just having a model, and depends that how good your model is, so you can add a lot of value in any business. As a matter of fact, just embedding AI into uh, its operations. Okay, and then so test sample is where you actually have an unknown sample, and you got to tell whether this unknown sample is going to be Y, yes or no, or if it is multi-model, then you got to find out the multimodality into this. So naive assumption is that every feature, so you got to be very, very careful in selecting feature, because every feature is going to get the same weight. So don't just include features that to you maybe, or that to somebody who's an expert in this area, um, who believes that this is not. For example, if it is a patient and issue, number of letters in his name is a very stupid feature to add into the list, because it definitely anybody would tell you that number of letters have absolutely has no significance in almost anything, except the storage that it takes in storing a name. Okay, so we have covered that is multinomial is where once the outputs are more than one. Okay, for example, if it is a disease, so you say it is early stage, it is middle stage, it is advanced stage, it is last stage. So if it is a disease and you are just doing a classification, and there are 4 possible outcomes, so it is multinomial if multiple outcomes are possible. Gaussians is if the outcome is going to be Gaussian. So we'll see an example here as well. And binomial is it is only yes or no. Okay, so there is a probability of success. We say P is the probability of success or probability of yes, and 1 minus P is probability of no. So if there are only 2 outcomes, then this is called the Bernoulli's naive Bayes classifier. Okay, so there are only 2 outcomes. So there is hardly any difference between this and this, only that only you have to calculate probability of yes, and probability of no can be derived from here. So please, if you could just turn off your mic. So P and 1 minus P. So you only have to calculate probability of yes or probability of no, and the other can be calculated from the other. So multinomial, we know there are multiple. Multinomial is where you have multiple outcomes are possible. Okay, and you make frequency tables to find out likelihood of happening one over the other. So it is Bernoulli's or multinomial. You got to calculate the probabilities using the data that you have. That you are not assuming any model, and this is the example we did. So we just colored it so that you can easily follow it, and I'll not spend much time on this. So the features are the color of the car, the type of the car, the origin, and then this is stolen or not stolen. So this is obviously this is Bernoulli's distribution, and you can calculate that how many times in your data the car is actually stolen and how many times it is not stolen but was taken somewhere for stealing something small in the car. So you have this probabilities, and now you go and start looking at every feature starting from feature number one and every possibility of that feature. Select, for example, red. So red, yes is 1, 2, and 3 time, and yes, no is 1 and 2 times. So you say probability of, and because this is a label data, so label data, this is already given that yes, red is 3 times out of 5, and given that no, red is 2 times out of 5. So that it is that easy, that because the labels are given. So given the labels, you can just only have to find out. You can make separate tables, or you can just see as I have colored them. So the yellow, similarly, you say yellow is 1 and 2 is yes, and green 1 and 2 and 3 is no. So it is 2 by 5 and 3 by 5. Similarly, and now you go to the type. So remember, this is your feature number one, this is your feature number two, this is your feature number three, and this is your label. So you say feature number two, sports, yes is 1, 2, 3, and 4. The red are 4. So 4 out of 6, and the green are 2. So it's that simple, like 2 out of 6. So you say, okay, these are the probabilities. Now the SUV, and again it is the red is 1 over 4, and the green are 3 over 4. So similarly, you go for domestic and make these probabilities, and the imported. So this is feature number 3. So now it is very simple because you are not going to calculate the denominator. So you only have to have the numerator. That now you are given that a car, somebody comes to the police station and says, I had this red SUV, which is not a sport car, domestic. So what are the chances that it is actually stolen? And based on the data that you have and the model that you have made, you say, let me just calculate, or you just put it in the program, and the program will come back and tell you whether yes or no. So how? Because it will say what is the probability that stolen cars were red, stolen cars were SUV, stolen cars were domestic, and cars were actually stolen in that area. And you just multiply them all, and you get this number. And then you do the same for no, because you have the same and you want to see whether yes is more prominent or no. So here you say, oh, it seems because it is 18 over 200, that is 6. So your car is not stolen. You will find out somewhere parked. Don't worry too much about it, because our record says these type of cars are not usually stolen. Right? So this is kind of the same thing you can do for customers, that if you have customer, that what type of customer enters in your shop, and if you have given him a membership card, so that means that you have also been collecting his data, and then you can collect some data from OSINT as well. OSINT mean from his Twitter account, if he's on Twitter, or on his Facebook account, if he's on Facebook. So you may able to find more features, and then you can just tell whether somebody is going to spend some money in your shop or not. So this is good. So the second example is a Gaussian knife based classifier, where you try to fit Gaussian, and for fitting a Gaussian, all you need to know is the mean, which is the mu, and the standard deviation, which is sigma. So, and then if you know these two features, which you can calculate from the data, And then all you have to do is just put it in the formula, and you can draw this binomial distribution curve, which is a bell-shaped curve. And then multiple features, if they are one-dimensional, would just look like this. So here is an example. So this is a patient, and his just one test, which is this PCA, and then these are the values of that test. And once the patient is declared that he has cancer, and these are the values of test when the patient is a healthy patient. And so this is the test, and here are some of the values for him to be declared as cancerous patient and a healthy patient. Just one feature. So this is just one feature. And based on the data, you think that is because it'll be difficult, or still you can make histograms and actually calculate the probabilities, that what if you make bins from 1 to 2, from 2 to 3, from 3 to 4, then 4 to 5. Okay, so you can have these bins as well, and 5 to 6. For example, this 4.1, you say it is in this bin. 3.1, it is in this bin. So 2.9, it is in this bin. 2.7, it is in again this bin. And 1.6, it is in this bin. Okay, so this is a distribution that you have. So you got to make buckets. So if you're not going to use Gaussian, you got to calculate histograms, and from the histograms you calculate probabilities. From the probabilities, then you have, for every bin you have a probability of that bin to happen if a person is cancer, and probability, for example, as you can see here, healthy patient 2.5, 2.0. So they have one here, one here, 1.7, one here, 1.4, one here, 1.2, one here, 0.9, uh, one here, and 0.81 here. So you can have, if you have bins, it's up to you. So you have bins, so two of here, two, three here, two here. And then total are 3, 4, 5, 6, 7. Out of 7 healthy patients, you have, so this probability 2 by 3, 3 by 7, 2 by 7. So probability of a patient happening in this bin, in this bin, in this bin. So you can calculate that. But better is, because you know that most of these things are Gaussianly distributed. So you make a generic model. You say, I see a lot of healthy patients here. So these are green. Green are all healthy patients, and they have patients with cancer. And these are the value of the tests that they have taken. And so you say, let me just uh, have Gaussian naive Bayes classifier. And now comes another patient. And before asking him to take more tests, you need to find out that probability of him having cancer or not. So it has low probability. You may not ask him to go and have advanced tests. And if you think that no, he has, a good chances of having a cancer, then you may ask him to go and take more tests, because this test perhaps is simple to take, will cost you little money. But these are the patients who, after taking all the tests, were declared that they either they have the cancer or they don't have the cancer. And now you have the actual data of patients with cancer and patient with not cancer, healthy patient, and the test. So you say, okay, I really don't know, but these are the patients who have cancer, and the other are who don't have cancer. So it's very simple that out of the healthy patient, you calculate the mean. We know how to calculate the mean. Add all the test values and divide by the total number of the healthy patient, which is 1, 2, 3, 4, 5, 6, 7, divided by 7. And we know how to find out the standard deviation. Okay, you take a value, subtract it from the mean and square it, and then add all of them together, then take the square root, then divide it by n. So I'll give you the standard deviation, because you need to have the average value in the standard deviation to know the distribution. So, and then remember that it's the formula. You put all the values of sigma and the value of mu here, and that will help you to plot the distribution of the patients that who are healthy patients. So this is the distribution, the probability. I'll give you the this is how the probability is distributed among the healthy patients. That healthy patients are This is how they are distributed on this test. Okay, so on average, a healthy patient, for example, has this test value. But there are cases a patient was found to be healthy, but he has very high value of that test. And very few patients has very low value. So mostly patient would have some value of this test, but it does not mean that they are cancerous patient. And then similarly, any so you say two means that this is, this is where he is on the curve. That so many people with two value are actually healthy people. So this is value 0.47. Okay, and then you do the same for the patient who have cancer. So almost repeating the same for the cancer patients, and you plot this. Okay, and now so this is the standard deviation. Now this is the guy who has come into your clinic, and you want to prescribe him additional test, or you want to say, don't worry, let's just wait because very expensive test. And you say, let me just find out where you stand using the base knife base classifier. So you have to find out the on his value on both the curves. So you say, okay, his value on this curve is 0.13, and his value on this curve is 0.47. So you have him on this curve, that how many people with this value were there, they were find out they were healthy, and how many people of this value were there who were found out they were actually not healthy, they had cancer. So you say, okay, and somehow it seems like this is the where both have like these the same value. So anybody who is on this part of the curve, according to this classifier, would be declared he has cancer. Anybody who is on this side would be declared is healthy. But you can see that even here there are few healthy people, and even here few diseased people. So this is where you have false positive, false negative, true positive, true negative. So all these people on this side of the curve and with orange are true positive. All these people with this type of the curve with all green are actually true negative. And here are this green guy is actually false positive. And similarly, this guy, the orange guy here is false negative. He has actually cancer, but according to this classifier, you may tell him, don't worry, just go and just sleep. You have nothing, right? So this is the cutoff. And so you will have some false positive and false negative, some healthy people declared as cancerous and some cancerous people declared as healthy, or so there will be some issues with it. But as it is just a first stage, so you with certainty you can just decide about what are you going to do. And then the uh, uh, so this is the label data. So you have this value 2.6 guy, so you can easily find out his probability that this guy with 2.6 PSA value, given that the cancer mean on this curve is value 0.47, and then you say, okay, and this guy same, his on the healthy curve is 0.133. So you calculate these two values, and then you got to have out of this data, you got to have that how many patients that who visited, and then goes for advanced tests were cancerous and healthy. So you say there are almost half of them were afterward you found out that they were healthy. And then this is the formula, because denominator, you don't care about the denominator. And you know that here is where you have the posterior probability, posterior about the health. This you have calculated, and this you have already calculated. And then you just apply this formula, which is the posterior numerator. And because they are independent, so you have probability that a person is healthy. Uh, so this is what you have calculated, that given a person is healthy, what is his PCA value, and the probability of healthy, probability that given that he is cancerous, this is the value that we have already calculated, multiply by 0.5. So you think that, oh no, you may have cancer, so you go and take advanced test. And so as we can also visualize that he is on higher probability that he may have cancer. Okay, so you calculate this and then declare that you may. And now people say, no, let me add another because I'm not getting like good results, and I am telling people who actually have cancer that you don't have cancer. Perhaps it has to do something with the age as well, and maybe you may add other things as well. Okay, so it is just based on some experience of a doctor, and he may say, no, let's have age as well. So now you have two features now. So obviously once you have two features, and we believe that they are independent if you're using base theorem. So you got to have like given cancer, the age, the given this, and you can have the same uh, Gaussian distribution for the cancer patients, their age, and for the healthy patient age. So now there are going to be two factors. One is their PSA, and the other one is their age. Okay, so two values. So you have to plot, let's say this plot 4.1 and 78. So say 4.1 and 78 is here. So this is the person has cancer. So similarly, you plot all the people who have cancer in a two-dimensional space and all the people who don't have cancer healthy in the two-dimensional space. Okay, and then independently you calculate this, that given that they are healthy age, what is the age, given they are cancer, the probability of age, and then you calculate posterior. And now these in posterior, you will multiply PSA given healthy and PSA age given healthy as two independent entities, and this will give you, may help you a little more deciding about whether a person who is old and has high PSA value has cancer or not. Okay, so you can go over all the numbers and the details at your own time. So I asked, I showed you this. I asked ChatGPT to generate a Python code to implement this, and then I also kind of ask it to um, uh, plot the data. So I've last time I've shown you all of this, that how it splits the data into training and test, and it is using it on iris data set, and this is how it is plotting. And then it also explains the code by itself. So you need to go and also look at how the code is being explained, and then the prompting it to also plot 2D and do the PCA and then do the Bayes theorem. So it would just do anything that you prompt it to do, provided you got to know, got to have this background knowledge that why not I try the Gaussian or the multinomial or binomial, or so you got to really direct, or maybe you say I am going to test the both to find out which performs better. And but so this is here I ask it to can you generate can a code be generated implement simple naive based classifier on self-generated table. So it has generated a table with many features: sunny and temperature is hot, and humidity is high, and it is not windy. So he will not go and play. So, and similar question kind of I've given you in the exam as well. So you have such table, and then it will just generate the code to implement the naive based classification. So, so we have another example where there are two features, the height and the weight, and who are adult and who are children. The black dots are the children. So this will also give you another just, and these are the adults. So now it is two-dimensional. If it is two-dimensional, obviously you first find out that in the population, what is the probability that you pick up some person who is an adult, and what is, so there are more children, so you have which data is more biased towards children, so you write that. So there's a probability that the children's, and then you just plot the height because they are now independent. So it seems they are not, but but as we know that we assume that they are independent. So you plot on one axis their heights, and then fill a distribution on the other axis their weight, and fill a distribution. Okay, and then so this is if they are independent, remember, they are not going to be a tilted ellipse. They are going to be an ellipse here. So it is going to be this ellipse. So it is according to the standard deviation of the height and standard deviation of the weight. So this is ellipse you are going to see, and where there is the same sigma on both sides, you're going to see almost a circle. So, and now here is this person, and you want to find out based on this data whether he is an adult or a child. So definitely you are going to do the same thing. First, you need to find out based on these, the average and their standard deviation of this to be an adult. And for all this distribution, the mu of the child and sigma of the child, and then you have the probability distribution of that given a person is an adult. So what is the probability? And similarly, you are going to find out a probability that given a child, what is the probability based on the sigmas and mu's that you have created. And now this point, you are going to project it on this distribution, and this point, you are going to project it on this distribution, independent of each other. And then two of these, yani first only on height and then on weight, if he is a child, and this on height and weight if you assume that he is an adult. So these are the calculations. There's a lot of calculations that you are going to do. First, as I told you, that you got to have a distribution for the child one and for the height, because this height is independent of the weight. So height is independent of the weight. So for the height, you do this distribution given he's a child. So you are having this formula is for this distribution, and then you have for the weight given a child. So this formula is for this distribution, which is for the child. Then you have the other formulas, like you have adult and height, adult and weight, and you are assuming that adults, the probabilities, they just multiply, so they are not correlated, they are not related, the height and weights are not related with each other. So for probability of adult, given adult, and its probability is you multiply these two together. Okay. And so now comes given a sample. Now this is an unknown sample, unknown unknown sample, and you need to find out what is the probability that this is an adult. So you say, okay, in case of adult, probability that given adult, what is the px and the probability of adult, and this you are going to divide it into two parts, and here are the two parts, the height and the weight. So it's and that's how you can just do the calculation. So though we covered it last time, but I wanted to just highlight it again, that is pretty much simple, and ChatGPT will very promptly will generate a code to just do this. Now, let's, because now we are going to focus more on supervised learning. And please remember, according to Andrew Ng, there are more business opportunities in supervised learning than in unsupervised learning. Okay, taking his experience in consideration, so we shall be focusing now more on the supervised learning. And in supervised learning, there are two things that you do. One is your classification, that you assign groups to the samples, and maybe a disease, maybe a type. And so you got to put a new sample into a class, okay? And it may be just only two classes, maybe multiple classes. Whereas regression is where you assign, you predict a numerical value. So this may be a stock price, temperature, humidity in the future, or it is maybe the rupee dollar exchange rate. So here you assign a value. So you have learned, so this is from the learning, you have this relationship curve. And once you have this curve, now you can actually do the prediction. And so the classification and regression. Actually, the classification also requires a line, something like this. Okay, this is a linear classifier. A regression also requires a line where you are minimizing. But there on this side, you want one class, on this side, you want another class for the classification. So usually all the algorithms which are used for the classification can also be used for the regression. Okay. So you can see this for the regression and classification. You have the same almost set of algorithm. It is linear regression, regularized regression, k nearest neighbor, and we have already covered decision trees. So you see decision trees on both sides. You see support vector machine on both sides, and so all these ensemble boosting algorithm, bagging algorithm, and then AI. So artificial neural networks. So they are on the both side. They can do the classification and they can also do the regression. So learning the algorithm will just help you to find out whether you want to use it for regression or classification and what is the difference. Okay. So we start with this supervised learning with perhaps the most basic and most intuitive algorithm, which is k nearest neighbor algorithm. If anybody has any question, please. So if no question, let's just keep moving on. So as it,
I have a question.
Gigi, please.
So, you said about identical events that they must be independent and
आपकी आवाज
identically
ना बहुत कट
distributed.
रही है. If you can just speak closer to the mic, maybe.
फिर अभी आवाज आ रही है सर?
जी अब आ रही है, अब आ रही है.
फिर आपने इंडिपेंडेंट एंड आइडेंटिकली डिस्ट्रीब्यूटेड चीजों का जो क्लॉज बताया है वो सर हमारी जितने भी इवेंट्स हैं उनमें सब में तो इस्लाम सब दो है मतलब भी कंप्लीटली इंडिपेंडेंट इवेंट यूज होता. मिसाल के तौर पर सर जो आपने ये हाइट और वेट का बताया है, हाइट जितनी हाइट ज्यादा होगी वेट की कंपेरेटिवली हम ज्यादा ही एक्सपेक्ट करते हैं तो वो इंडिपेंडेंट तो नहीं होते और डिपेंडेंट नहीं होते. और हम कोई भी मैंने एक और एग्जाम्पल दी थी ब्लू और रेड बॉल आप एक बैट से निकालते हैं तो आप एक रेड बॉल को निकालते हैं बाकी ब्लू बॉल और रेड बॉल की तो उससे करते हैं इससे वो सारे डिपेंडेंट नहीं आपस में.
जी आप सही कह रहे हो. इसीलिए ना ये जो है हमने इसको दिस इज व्हाट वी आल्सो लर्न के ये जो टाइप है ना नाइफ बेस, इसमें आप एक बहुत स्ट्रॉन्ग assumption कर रहे हो which is usually not true. But it still would give you good answers because you are just classifying things. Okay, you're just making a problem simple. So for example, sometimes you make a problem simple. You have this, and you can, if you are asked to, especially this line which would require maybe 4-degree polynomial, and you say let me just approximate it with a straight line because straight line is simple. So you make a problem simple to represent because perhaps you want to only see a trend that whether it is going up or down. So is the case. It is the naive based. You are making an assumption which you know that it is not true, but because you are not really too concerned, you are not modeling it. So if you are creating a model to generate more samples, they maybe you may be more careful, and as we have been once we were doing Gaussian mixture model. But here it is just a matter of classification, yes or no. And if you have a labeled data, you can see how good it is performing. If it's performing good, you say I'll use this simple classifier. IID was a bit different here. It was we were selecting samples from a set, and we just want to make sure that independently, and we basically select samples from each bucket, so that once we are doing some experimentation, we have true representation of data. So okay, so this they do depend upon the features do depend upon each other, but just to make a problem simple to solve, we do this approximation. And you have the data because assumption is that in supervised learning you have a lot of data available, and so you apply and you find out that it's so poorly performing. So now there are more sophisticated algorithms, so you say I'm not going to use it, I'll use more a better algorithm to do the classification. And that is the whole purpose of learning, that you have to try all different algorithms to find out which one works best for a specific application that you are targeting. Okay? So for example, this is again a very simple algorithm, and it has like good applications in robot pick and place application, for example. So mostly robots, they have a camera, installed on their end effector. So this is the end effector. So there is a camera. It is taking picture. It is conveyor belt. So whatever is coming on a conveyor belt, it is taking a picture. Okay, and now you got to do a classification. If it, what type of part it is. Okay, so usually camera taking a picture, going to your computer, maybe a server where you have developed a classification application, and now this classification would come back and tells it that this is the part. So the end effector will know how to basically pick up that part, and this is also called a pattern recognition, machine vision, a pattern recognition application, or vision, machine vision application, where machines actually don't have eyes. Okay, don't have eyes, but you got to have a classifier depending, because you know that only it has, you have to figure out that what type of object is there that is to be picked up. So for example, here are some of the mechanical components, and you want, and they are just the end effector has to, you ask it to put a bolt or a nut, and this is the bolt, for example, and an effector has to figure out where the bolt is, and so that it can just go and pick that up. So it's a complex kind of a machine vision application. Okay, so these are, for example, different parts. And now you are sitting and you are thinking that obviously you have eyes, so you can find out that what this part looks like, what this part looks like. uh, the robot does not have an eye, it just has a camera, and camera image has to be fed to an algorithm, which is a machine vision algorithm. And machine vision algorithm usually has to somehow, if you want to make it very simple and low cost, has to extract some features. Okay, so you need to extract some feature of every object. Let's say your problem is simple, and you say I have parts which has some area, and there is a hole in the part. There is another part which has holes. Then there is another part. Then there is another part which has, okay. And you say I have like from I is equal to 1 to n different parts, different types. Okay, and you don't want to use a deep neural network to do such a simple problem, where you only have to classify, let's say, out of 4, which one is this, or out of 10 or 20 and 30. And so you decide that you will just pick two features, and maybe you say I will pick the total area of this thing, because you have a camera is taking a picture, and you can do the segmentation, image segmentation. You find out this is the total area of the body, and then you say here is the area of the hole, which is a circle. And so you have the total area of the holes. So here you find out the total area of the holes, total area of the holes, total area of the holes. So once you plot them, you see, oh yeah, they are largely, they are widely separated. So I am fine with only having two features, which is total area and area of the hole. And you plot every, so you have this golden standard, gold standard parts, and you plot gold standard 1, gold standard 2, part 3 part, based on these two features. And now your problem becomes a very, very simple problem to solve. So you have this part coming in, it takes a picture, it finds out, yes, there is a part, it segments it, it figures out how many circles are there, and find out the area of the circles, find out this, and just plot it on this 2D graph. And obviously anybody would say just throw it on this. There may be some a little, manufacturing artifacts which will not precisely map it onto 1, 2, 3, 4, or 5 parts. So it may be somewhere here. And so if it is here, it is closest to 1. So I will say uh, the robot will say it is 1. I think the Azan is going on. Let's just wait 2, 3 minutes, please. Okay. Okay, so you will just say this is 1. So, and similarly, if it is closer to 3, so this is k nearest neighbor. This k is equal to 1, so it is closer to 3. You say it is 3. Now let's say you just keep plotting, and you have a lot of parts, and at this time you are just doing training, and then you're finding out like there's a lot of manufacturing artifacts, and because of that, this is like, though it is still in a cluster, but it's like spread out, spread out, spread out. And here comes now a part, and now you are kind of confused whether should you assign it to 1 or 5 or 3. Okay, so the k nearest neighbor basically is a type of algorithm which will just help you out in this particular scenario. And problem becomes more complex if there are many, 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 many types, and there are many, many, many features. So it becomes an algorithm which will not give you good accuracy. So KNN is non-parametric. So you are not really calculating any parameters like mu and sigma and distributions and their contributions and nothing. Okay, so there's no parameters, there are no weights that are to be trained. So it's kind of, there is no training except learning that this is the all the data that you have, and you have to store it. So it's a supervised learning classification. Especially you may need to decide about the k, and we'll find out what k is. Uses proximity to make classification or prediction decision. So the neighbors, you believe that all those birds of the same feather, they are at the same location. So anybody which is closer, you just assign it to that. So assign class based on majority of the neighbors. Okay, need distance measurements, and need to choose k number of neighbors. Note k must be odd for simple majority. So for example here, you have this one type, the green and the red. Okay, and you have like two features. There's this feature x and y, and you want to decide a label for a and for b. And it's an interesting problem, because if you see, you say the nearest neighbor, you say nearest neighbor of a is going to be green. So you say if k is 1, that I'm considering just the nearest point, then x1 is assigned to green. But then you say, what if I consider radius is equal to 3, and then green is only 1, whereas red are 2. Okay, if you consider the nearest neighbor is, you believe so your nearest neighbor should be at least 3 of radius 3. So you find out that 2 are red, so this you will label it as red. But you say, if I'm saying 3, why not I say 5? Okay, as you're moving away, obviously you are kind of assuming that your spread is much wider, and you say, oh, in this case a again is green because there are 3 green and only 2 red, so you say it is green. So means that this is what you have to do to find out the value of k. And the training set, that you have the training set, so you have the data, you split it into training and the test, and then you just find out that what k value of k gives you better results. So here is that what we have seen, that again majority voting about b is, if it is just nearest neighbor, you are going to say it red. If it is 3, you are still going to say it red. But if it is 5, you are going to say it green. So that is something you got to decide whether how to choose k is the thing. So you can have many, many different examples depending upon the types. And here comes this, so you need to decide that how many nearest neighbors. So somehow it is also kind of computationally, becomes computationally intensive, because you have to take distance of this point from every point, you got to sort it, distance of this with every point, you got to sort it. And then you have to decide whether k is equal to 1 or 5 or 3 or 7. And then you have 7 neighbors, and out of those 7 neighbors, find out which one is appearing more. And so you have to say, okay, it is of this type. So this is Simple, very, very simple algorithm. And depending upon the application, you can decide about the distance. So we know Euclidean distance, where you have every feature. So I is equal to 1. So you have feature 1. So there you are assuming n features in the data. Okay. So you take first feature of this point, which is you don't know what it is, and this point. So you have this data point xi, and you have this yi. So you do the subtraction, square it, and then keep doing it for feature 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If there are 10 features, so and so you do this and then take the square root, it will give you the distance between 2 points with n features. So this is, you are assuming n feature, and sometimes you may have to normalize. So one feature may be like some small values, the other feature may have very large values. So you don't want it to be biased by one feature, so you may want to just normalize it, dividing it by the maximum value, so that every features run from 0 to 1. And here is Manhattan distance, where you just take the uh, not, you don't take the square, just the absolute value. So every feature minus x-axis, y-axis. So here you are just taking the absolute value of the feature. For example, if, and we know like 1 and 2, and this is 3 and 4. So it is 4 minus 2 plus 3 minus 1. If you do this, they are the absolute value, it is Manhattan. If you take the square of this and square of this, it becomes the Euclidean distance. And then there are other Minkowski distance, where instead of taking square, you take power of p. Actually, here is p, and then overall you take power of 1 over p. And then Hamming distance is usually we use in digital communication, where you have bits. So you have 8-bit number, and you say how many bits are different. So these two bits are different. Here it is 1 and 0, 1 and 0. Rest of the bits are same. So your error is 2. Okay. So this is called the Hamming distance. It's called the lazy learning model, because it just sits and consumes a lot of memory, because the entire training data it does not really remember. In Bayesians, you convert it into mu's and sigmas and the probability. So you actually have a model. Okay, but this does not have a model. You got to have all the training data. Okay, and you got to have then computation occurs when actually you need to classify. So it requires to store all the data. Heavily relies on memory. So this is the KNN. Interestingly, once the data set grows, become increasingly inefficient, compromising overall model. So many parts, and they spread all over. And it is only used for like simple application. Once you have simple data, maybe recommendation system, pattern recognition, data mining, financial market, intrusion detection. So it is very handy, very easy to comprehend. And definitely you can always try to see that how KNN is performing in your specific. So he, so you can just see, like, obviously such a simple idea. So it was invented actually in 1951. So this guy has the paper. So I went and figured out that this paper, and the paper says nearest neighbor pattern classifier. So this is another guy. He's another paper who published it little later, and there they have to actually unclassify it. So it is says non-parametric description consistency properties. So it revealed this algorithm by actually having this unclassification. So perhaps it was though done by some university research, but apparently it was used in an application which perhaps was for some naval application. So they got to actually unclassify it to make it accessible to public. But then this guy, and this also tells you how to make something simple very complex and publish a paper. Okay, so it is a nearest neighbor pattern recognition. And what it has done is it says, okay, nearest neighbor is there's distribution, point distribution, there's point, another class, another class, another class. Okay, and here comes the point. And there definitely there may be an error once you are just assigning it to a class. And then you can also use Bayesian theorem or Gaussian mixture model. So you can have a probability distribution, And so underlaying joint distribution on the sample points, and he is just trying to find out that if you compare it with the probability distribution, what is the error margins. So bounds are the tightest possible. So you see a lot of math in this paper is doing, and he says here, the nearest neighbor rule is bounded above by twice the base probability of error. Okay, so he has like this, but he's just comparing it with the other classifiers, and it's a lot of maths if you look into this paper. So I would urge you to just go and download it and see. Just if you type this, perhaps you will get a access to this paper. And selecting K, I told you, there you can do a lot of experimentation with the data you have. The choice of K largely depends upon the input data. Data with more outliers or noise will likely perform better when higher values, because there is an outlier. Outlier means that's a noisy point. Okay, so you have this, and for cancer, for example, but this is an outlier, and you are just finding a nearest neighbor, so you'll take a wrong decision because this is an outlier. The other were around this were the other from the other class. So outliers will affect your decision. Must be an odd, and cross validation can help in choosing. And now we need to learn about a little about what this cross validation is to find out the K. So I use ChatGPT. I asked ChatGPT to generate Python code that demonstrate KNN classification technique. So it generated this code for me. Okay, so it has this is favorite data set, iris. It loads iris data set, and it is a labeled data set. So it has a data and the target, and then it splits it into training and testing. So it is the data split. 70% kept points for the training. I think there are 150 data points, and then it has like 30% of them for the test. So split into, so this is the function it uses to split, and then it has fixed k is equal to 3. Okay, and k neighbors classifier is there. So here he has imported the k nearest neighbor classifier. All it has to do is now put this and put k is equal to 3. So KNN is now loaded, and now you say KNN dot fit the this data, which is for the training, and then KNN do the prediction, and it does that, and then we have the accuracy score. And now comes a new sample which has this length of the, remember there are four values, there are four features in this data. It is length and width of the petal and length of width of something else. So four features. So giving the four features, it asks what type of flower iris it is, and it will say it is Setosa, and it says accuracy is 100% accurately it could do the classification out of the training data you have provided it. Now I wanted it to know that can we also plot the points to demonstrate the algorithm. He said yes, why not. He so just change the code, and now you see all the points. So here are the training data. The circles are the training data. So you all the circles, all the circles, all the circles are the training, and now are the testing. So for every testing, for example, this is a testing data, and depending upon three nearest neighbors, so 1, 2, and 3 nearest neighbors, so it is going to say it is red. So here is the training data. Okay, so the training data will go through the algorithm, and this has it has made like this type of boundaries for the three classes. Now so now because it's I wanted it to do the cross validation and find me the value of k. That requires us to learn about how actually you plan once you have decided that you are going to develop a supervised learning application. So what are the steps you go to develop a supervised learning application? So first thing is that you got to have labeled data. So this is your data set. If you are targeting a potential, a commercial, client, you go and you collect data for the client. Okay, this is very important, and he may give you the data. So, but the data set is most important data. If it is a hospital or a business or or even voting, elections, you're making election strategies, and so whatever you want to do. Uh, Pick almost anything that happens in this world, and you say, I can perhaps make you do I can increase your profitability by actually having access to the data set, and I want a labeled data set. Okay, it says, okay, here's the labeled data set. So you say, okay, now I have labeled data set and it is a large set of data. So I think I can have a good model to help the person in making decisions. So you now split the data here, just randomly select, let's say 70%, you keep it here to train the model, and 30% you say, I will assume that this does not even exist. I assume that I have deployed my system, and now the new customers are coming or the new patients are coming, and I'll see that how good my model performs on this, because you have randomly selected this and you have closed eyes. You have just you need to hide this. Okay, you must never use this to validate that how good your to test how good your model is. So this is, you're not going to
Sir,
see.
excuse me.
जी जी
Hello.
जी जी बताएं बताएं.
First, sir, इसमें how we will determine that how many samples we need to choose? So what is the minimum level? For example, if we
जी.
have 10,000 samples, so how much data would be required where we can say
Okay.
that yes, here we can get the optimal results?
Yes. So, I mean, this is very good question, that how do you decide that amount of data? This step will tell you, for example, you have like very little data and you train a model, and once you test it, it performs poorly. Okay. So it means that you don't have enough data to make a good model. There may be cases which you don't have, like those cases happening in the data. For example, you are classifying like out of 10 different diseases, for example, and now you have data, and there was hardly one or two samples of one specific disease. The model is not trained on that, and there may be two three samples in the test data, and they will never be correctly classified because not enough data was there. So there is no rule, there is no math which will tell you that how much data should be there. But the trick is that this step will tell you whether you have enough data to train a model. If not, then sometimes now what people are doing is they go to the generative AI, say generate more data for me, which should look very realistic and should make a model of the data and just learn the probability distribution and then generate more samples so that a classification algorithm can work. Okay.
Sir,
So,
here can we follow? Sir, excuse me. Here, sir, here can we follow, because in research we say that if we are going to conduct a survey, so at least 100 samples we need if we want a significant result. So could we
yeah,
apply
so
that rule here?
not really. Look, it depends upon the application. Okay? For the survey, for example, they say you want to find out the popularity of a specific party, maybe it is PTI or Pakistan Muslim League, no? And you must have found people just taking a mic and just they're going on the road asking everybody who they are going to vote for. And this is randomly, so they are just randomly selecting, and then based on that they are saying, okay, this much percentage for PTI, this much percentage. So the people who conduct survey, okay, and they have like some figured out that if you have only these many samples out of a population, and where IID, like you have almost gone to every class of people and have selected few of them to answer, so that should be enough. That should give you something which is closer to the reality. So perhaps they may have, by experimentation, they may have a number that perhaps only if you have 10% of the population or 5% of the population that you have surveyed, and that is a good reflection of what it actually is. Okay, so maybe through experimentation, experience, through maybe the modeling, they may have figured out that this is a good number. But again, it depends upon application. It varies from application to application. So there is no definite answer but there are answers, like if you have more data, you can do deep learning, but you have less data, you cannot do deep learning. So you use the other type of classifiers. Okay? But if you have humongous amount of data, then perhaps you don't need to put your intelligence into the model. Just let the model figure it out by itself, that what should be the algorithm, the underneath algorithm. As you can see, up till now, we are actually dictating in the CN trees, in KNN, in Bayes theorem. So we're doing a lot of calculation. We have some assumptions. So we are actually designing an algorithm. But in deep learning, you usually are not really the one who is designing the data and humongous amount of data, but that requires a lot of data. If you have a lot of data, and then you let your model learn. But this is what will tell you how good you are. Okay, so usually what we do is that you have this data. Okay, let's say you have 10,000 samples. Samples mean 10,000 patients data. Okay, and you are going to figure out whether a person is diabetic or not, for example. And you have 10,000, and you have every patient has some features, as I mentioned, his weight, his height, and his maybe uh, the blood pressure, some of those features. So, and you know whether that person is diabetic or not. So you got to have label data. In this, label data is very important. So once you have label data, you leave for example, 3,000 to test your algorithm and 7,000 to train the model. Out of this, again, you have this K folding. Out of this, let's say this is 5 folding. So 5 folding means you split this data again into 5 parts. 1 part, second part, third part, fourth part, 5 part. Okay, out of this 5 part, you again leave one for the validation. Okay, so 4 of these you will use for the training. So do a lot of iterations to train it, and then just one part that you will validate whether how good your training has happened. And this is for algorithm 1, you do this, for algorithm 2 you do this, for algorithm 3 you do this. So all the algorithms and their variants, you have Bayes, naive Bayes, KNN, a sport vector machine. So you can have many algorithms, and then means every algorithm means a model. So this is model 1, this is model 2, this is model 3, and you want to check which model suits best for this specific application. So you tried all the algorithms, and within that algorithm you can try different parameters of the algorithms that you got to tune. So you run many times it here. You have a model and a result, that how good you are for the accuracy and the other things that we have already talked about, recall and precision and all of that. And depending upon whether you are focusing on recall or you are focusing on precision or accuracy, and so you get some result here. For every algorithm you get some result here, then you go to this one, and now you are using this for the testing, and you are hiding this to validate how good you are performing. And then you do this again, and now this and this and this. So you run it. If it is, let's say, 5-fold validation, it is like this. If it is 10-fold validation, so there are 10 set of data that you basically split and run the algorithms, and then you find out that which model has performed best over the entire data set. Okay, over the entire data set, this is my model of choice. And now you take the training data and run the training data on that model to find out, is it performing really good? If it is performing, you say, wow, this really performed good on my test, and so I'm going to deploy it. Okay, so this is how you do the your planning, that you split the data into 3 parts: your training, your validation, and your test. And data is split further into K folds, and it does not work well for small data set. A really small data set, it really does not make any sense to further split it into so many folds. And so every fold gets chance to appear in the training K-1 time. K is generally from 5 to 10. And if you keep K large, like some people say, leave one out. Leave one out mean out of the data you have, you leave one out, do the training validation, then leave this out, do the training validation, leave this out, and include everything in the training. So that's called leave one out cross validation technique. So then One is the average performance. The model's performance across all k folds is assessed, that this model A1 algorithm has performed on average. So you calculate accuracy, you calculate precision, you calculate recall, average accuracy, average precision, every recall. So this is how you're going to select your final model, because you have tried almost everything, whatever you know, because you don't mind just trying everything out, just so that you find out which one really works best for you. And then you say, okay, algorithm 1, algorithm 2 has done, algorithm 2 has performed like this, algorithm 3, model 3 has performed like this. And based on the average value, you may want to say, okay, I'm going to select this model, which has the best average performance. I'm going to choose this. Or you, instead of just best, you say, I will go for the variance. Like if an algorithm is performing very well on the first fold and on the second fold, and but performs poorly on the third fold, so its performance is good, 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 and then it is very bad, and then good again, and then again very bad. Okay, it's a lot of variance. So this is called variance. It is performing well, and then it is not performing well, but on average it is high, because once it performs well, it performs very well. So you say, no, I want my algorithm to be more consistent. I don't want it to perform 100% and then 70% and then 70%, then 100%, then 100%. Okay, I would rather have an algorithm which is consistently performing 85%, for example. So you go for, so this is called generalization ability, that you're going to select a model does not show variance. So you got to select something which is not showing variance. And so variance is important. It's not having significant variance uh, between the different fold. Or you may just go talk to somebody who is a domain expert and discuss with him, and you may yourself get more insight into seeing that perhaps this type of algorithm, as we were discussing, you say perhaps the naive base is good for me to for this particular application. And sometimes you're worried about model complexity. You say, though this is performing well, but I have this edge device which is going, because I've gone to a customer and he says, okay, this is my problem. And you say, I'll put a very simple microcontroller, so this tiny ML, and I'll just run a classifier there. It'll take very little power, will give you decent accuracy. And you say, no, it's such a complex model. I have to run it on the cloud. So I have to bring all the data to the cloud. So it adds a lot of cost to your solution. So obviously, the model complexity is another thing that we need to be worried about. And then is the computational resources. And so the computational resources obviously is important. So there are many things before you decide that which model are you going to use for a specific customers, because you may have constraints. You may have constraints on the resources that you have, the storage that you have. So they may be, so it's not the best that you always select. It is the based on a constraint, you find out which one is the best out of those. But while you are training, you want to just explore the entire design space to find out that how good you can perform. And then you say, though I can perform very good, but this is what I am going to use. I think let's have a break. Let's have a 30 minutes break, and then we meet again. ठीक है जी?
Yes, sir.
Sure, sir.